All right, let's continue. We are probably not going to have time to go over the overlay algorithm, but I'm going to at least plan to finish the doubly connected edge list data structure. And maybe start define the problem. What is the overlay problem? Okay, so given a plane like this, consider this blackboard. You want to identify regions on this blackboard. Okay, so how do you represent regions on this blackboard? What do you do? You just draw these regions using line segments, for example. Like, okay, I have a region here like this, another region here, this region. Okay, try to think about complex regions. Maybe okay. Let's divide it something like this. I have a region here which has another region in itself. So the question is, how do we represent this on a PC, on a computer? What kind of data structure is needed to be able to represent? Means that, I mean, you need to able to store what you have drawn here, and you should be able to recreate the same picture by using the data you have stored. What do we need to represent this subdivision, these regions that I have drawn on the board? So what do we have? For example, we have vertices, right? Like the endpoints of these line segments. In order to say that I have a region, a square region at this point, I need to have vertices with coordinates. They need to have coordinates. Okay, so vertex 1, vertex 2. What else? Edges that connects these vertices. I have an edge that connects them. And four such edges define this face or region. Okay, so these are the three entities we are going to be using: vertices, edges, and faces. A face is a region, possibly unbounded region of plane, because we have a blackboard here, which is a bounded entity, this blackboard, but in general, we are going to be define a subdivision of a plane which is infinite. So you may consider outside this board is also part of an infinitely extending plane. This board indicates a certain region. And whatever outside this board, you may say that that's the unbounded region outside this board. So we are going to have a single unbounded region outside. You can consider this part, okay? Just forget about the boundaries of the blackboard. This region, for example, the best way to talk about regions is, remember the paintbrush program? They have this bucket function, which you just, in this bucket function, you click on a certain point, and all the reachable points out of this bucket, out of this point, are colored with that whatever color you have. Okay, so we can define region in that way. So if I, for example, use that bucket functionality here with the color red, for example, where are we going to color red? Which regions? That's going to define my face, my region. For example, if I do it, for example, if I say that this face F is going to be my unbounded region, and when I click any point on this, if you try to paint this with the red color, where are you going to reach? So, in other words, what entities bound this region? For example, what prevents this red color to spread to the other parts of this plane? We have, for example, in this unbounded region, it doesn't have an outer boundary. So since it's unbounded on the outside, this F face, it is bounded by other edges and vertices of this subdivision. This other edges, for example, having this region, which is the outer boundary of this face, that we call it F1, is actually bounding our outside face. I mean, the red color is not going to be able to spread inside this. This region is going to be a hole for the outside face. Okay, so it's a face with holes in it. So everywhere is going to be red except here, 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 and here, because these edges bound my face F from the inside. In other words, they are the holes of my face F. And one such hole can be the outside boundary of another face. Okay, a hole can be also considered. For example, if I say, okay, now let's make this place blue, and this is going to be a blue face, and this blue face is going to be bounded on the outside by these four edges. Yes?
We said we have vertices and S, but maybe we have some curvy things also.
We are not going to deal with curves here in this planar subdivision. We can have curves. I'm going to assume that each curve can be represented by a series of line segments. Okay? They can be approximated. Even you have a circle, you can approximate your circle with a set of line segments. So all we are going to have straight edges. So our edges are going to be straight. But in general, your edges that bound surfaces can be curved. But they can be approximated by linear, smaller line segments. Okay, so, and I draw, most of the things I draw here are convex. I can have concave things as well. Okay, I can have something like this. What about an edge like this? That doesn't go anywhere. It's not, I mean, it doesn't, it's not a part of a closed surface. I mean, it's just an edge. So this is not considered a hole, but it's again, we cannot, the outer face cannot have a point. I mean, this is not going to be colored red. Whatever original color it has, my color changing will not be able to change its color to red. So my face is not going to extend to this edge and to this point. So what happens is that a point P is an element of this face F until it reaches a vertex or an edge. I mean, the vertices and edges are not part of this face, and all the points that I can reach from point P here, for example, is going to be part of this face F. Now, what kind of a data structure we can use, as the name of this lecture is doubly connected edge list, is a suitable structure for this, for representing such subdivisions. We call these such kind of objects, I mean such kind of region representation, a planar subdivision. And this planar subdivision sometimes may be connected. I mean, if all the vertices connect somewhere, for example, they're all connected to each other, we can have a connected subdivision, or we may have a disconnected subdivision, as in this case. This division, for example, this region is not connected in any way to other regions. They're all connected to this infinite face, unbounded face, but in general, we can distinguish between connected and disconnected subdivision, but we are not going to talk about this connectivity in the rest of this chapter. So now let me describe you the doubly connected edge list data structure. We note that, consider this hole. We said this was a hole. This hole, which is an inner boundary for this face F, is an outer boundary for face F1. Okay, a hole is also a face. Okay, I mean, if you consider a point here, it belongs to this face and it's bounded by these edges on the outside. So usually when we talk about faces, we are going to be talking about two different types of boundaries. One of them is going to be the outer boundary. Each face is going to be bounded outside by a closed boundary. Okay, it has to be. I mean, if it's not closed, it's going to be an unbounded region. For example, imagine we have something like this. Yeah, just like this, for example. It's just a set of line segments which are not closed. It doesn't define anything. So actually, as you see that, this face is not different than face F. I mean, if you try to click here to draw to paint everywhere red, this region itself is going to be also painted red. So it's also, this region is an unbounded region. It's not bounded by an outer boundary. So it's the single unbounded region of this planar subdivision F. So this is also an interesting property. Maybe I don't know whether they have it as an exercise, but it may be interesting to prove that any planar subdivision of a plane, of an infinitely extended plane, has only one unbounded boundary. Okay, so this may be interesting. I mean, you should be able to prove this. Probably proof by contradiction. It seems that if they are both of them are unbounded, it becomes, I mean, they become the same region. They cannot be. There has to be some line that separates these two. Oh, maybe, yeah, that's an infinite line. Okay, that's a good point. Now it questions about our it raises questions about our definition. In this planar subdivision, do we have line segments, finite line segments, or are we allowed to have lines that extends to infinity? For example, imagine this whole plane is divided by this line that extends in. So our plane becomes two half planes, so two unbounded regions. So our claim is not wrong. Is not correct. If you have a line that separates these two, this half space is bounded by this line, this half space is bounded by this line, so they are two different unbounded regions. But let me change my proof like this. If all of our edges are finite length, edges with two endpoints, they are not infinitely many. They are not edges that extend to infinity. If we have edges like this, like that, can we say that in any planar subdivision we only have one unbounded face? This statement should be correct. But I mean, we may need to prove its correctness. I mean, my inclination is that it's probably a correct statement, but we may need to try to prove it. Again, proof by contradiction probably is going to work in this case. So,
unbounded regionlarda planar subdivision olarak geçiyor mu? Unbounded
yes.
region bir tane olmak zorunda değil mi? Zaten yani hani domain bir tane.
Yes.
Her şey
Yeah, the unbounded region is also. So the planar subdivision, our planes are, when we consider the plane, it extends to infinity. It's not bounded by anything at all. So we have a one unbounded region in this plane. So when we start drawing things in this, we start defining bounded regions with bounded by some outer boundary. But you may think about, I mean, you may say that, okay, this unbounded region is usually the useless region. Now, why do we use such an unbounded region? Does it have any meaning, maybe? Usually, in real maps, if we are going to think about a practical application, we are going to have some bounded region. We have the boundary of the map is the one that has this region. So if we have something like this, for example, this is not a new face like F2, okay? This new face is the same as our unbounded face F, because F extends here as well. So whatever, except the unbounded region F, all the regions that we define here are going to have a cyclic outer boundary. Okay, they are going to have all the regions that we define in this subdivision, they are going to have an outer boundary which bounds them on the outside. Okay, if they are not bounded on the outside, it means they're part of this unbounded region F. So every region that we define, it's going to have, for example, consider this face F4, okay, this face here. It is bounded by these edges, and also it is bounded by this hole inside it. Okay, so this region, when I define this F4 region becomes this. On the outside, it is bounded by these edges, and it also has a boundary on its inside. Every region has one outer boundary, but they can have multiple inner boundaries. For example, I could have a separate hole here. Okay, this separate hole also bounds this region. We cannot get inside this triangle. So it's going to be a hole. So we can have multiple holes. A face may have multiple holes. And what we consider a hole here is actually the outer boundary of another face, face 5, for example. If you consider the inner region of this boundary, it's, these edges are going to be the outer boundary of face 5. Now this shows that, I mean, this edge sometimes act like an outer boundary and sometimes act like an inner boundary. So this, therefore, we need to give, in order to define whether we are in an outer boundary, what is our face? When we are walking along an edge, where is my face? Which face I'm associated with? To be able to, if an edge asks this question, to be able to define it uniquely, we need to define an order of traversal to define where your face is located. So, and we are going to, this is not a universal rule, you could have defined it differently, but the book's convention is that, and we should decide on something, a unique direction. When we walk along an edge, its face is on its left hand side, okay? So, in other words, when we are walking on the outer boundary is traversed counterclockwise for that face. For a face F4, for example, its outer boundary is consisting of edges, which can be traversed counterclockwise. For all these edges, this face is going to lie to the left of these edges. Whether it's convex or concave, it doesn't matter. Okay? For all type of objects, the face that is incident to this edge is going to lie to the left of it. Now, for outer boundaries, we have done with, I mean, this solves the problem for outer boundaries. What about inner boundaries? If we traverse the inner boundary again counterclockwise, for example, if we traverse it counterclockwise, if this is an inner boundary, its face, I mean, if we consider this as an inner boundary, its face is this, okay? So if this is an outer boundary, its face is F4, and if this edge is part of the inner boundary, it's the inner boundary of F4 still, okay? So it's for holes, we see that we need to change the order of traversal, because when we are again traversing counterclockwise, our face, the face of this edge does not lie to its left. It lies to its right for inner boundaries. So we have this rule now. if we have an outer boundary cycle of edges, they are traversed counterclockwise for a face, and their inner boundaries, the edges on their inner boundaries, holes, are traversed clockwise for that face. But for face F5, since for F5 this was the outer boundary, then we need to, so this for inner boundary we are traversing it clockwise, but for face F5 we need to traverse it the reverse direction counterclockwise, so that this is an outer boundary of face 5. So we need to be able to traverse a cycle in both directions. And therefore, hence the doubly connected edgeless come. We need to, starting from a vertex, we need to, these two edges, okay, we are going to have two edges for a certain, for two vertices. And these edges are going to be called the twin edges. They are going to be called twins. One of them is going to be the outer boundary of some face. The twin of this edge is going to be the inner boundary of another face. And in order to be able to traverse the, along the boundary, we should also have next pointers. If I'm on this edge, I need to know what is my next edge in order to complete this traversal. Sometimes we also need a previous edge. Why do we need a previous edge? Just maybe to make sure to check whether it's a closed boundary or so. We may need a previous edge as well. I cannot really recall why we need previous edge. Can you think of a reason when we are storing the edge records for an edge and for a half edge? We are going to name these edges. Also, let me mention that since it has twins, this undirected edge is the original edge. It has no direction. It is just the edge between two vertices. We divide this undirected edge into two twin edges, and each of them with direction are called half edges. Okay, so we have half edges, and we have twins. So these are called twins. Okay, and for an edge record, what we need is, in order to locate this edge on this map, we need its coordinates. So we need to associate with a vertex. We need its origin. So each half edge has an origin vertex. Okay, so this origin vertex, and if I have a pointer to its next half edge, for example, if this is the next half edge, I don't need to store a pointer to this other vertex because the origin of the next half edge is going to be the destination of the other edge. Okay, so I'm going to now, after all these descriptions, so we have this defined twin, half edge, origin and destination, and we have defined holes and everything. Now what I'm going to do is I'm going to make this data structure more clear, I'm going to draw this example subdivision on the book and the records associated with that subdivision. I mean, what I have drawn here, just to make it a complex subdivision, I have just, it looks like really a cubic art. So I'm going to make it more neat and tidy, a simple subdivision. Yes. Yes. We are going to see in this example, we are going to have some edges which do not go anywhere. We are going to still store their edges, but they may not be associated with any face. They may be associated with the unbounded face, maybe. Possible. Very good question. I mean, I showed you two holes in one hole, but I never showed you in my example hole inside another hole. Okay, we can have something like that perfectly. Now, how many faces do we have here? Just think about this bounded region. We have face 1, face 2, and face 3, right? We have 3 faces in this subdivision. And this phase 2 has one outer boundary and one hole. And phase 1 has only one hole, which is, so phase 1 extends only this region. So phase 1 doesn't no knowledge about this inner hole. It doesn't need, because it's only bounded by F2. So therefore, we don't need to have a hierarchy of holes within a single phase. All this phase need to know is what is bounding itself. It's the only thing that is bounding F1 is F2. So its inner boundary is going to be F2. It doesn't know anything about F3. Okay, it's not an inner boundary of F3, the second inner hole. Because F2 already contains F3 itself, so knowing that F2 is its inner boundary already contains all this information. We may even try to find the doubly connected edge list record for this example. I'm going to do it after I do the example on the book, and I think I'm going to leave at that point this week. Okay, the example is easy actually. So we have these are my vertices. Okay, my subdivision is just this. Now, in this subdivision, I have two faces. Okay, F1 is the unbounded face, which is the blackboard. I mean, it may consider it is bounded by the edges of the blackboard. And I have another face, F2, which is bounded by these three edges. And I label the edges like this. If this is my first edge, if this is edge 1, I also say, okay, this is the first F of edge 1, this is the second edge. So the twins are indicated by these indices 1 and 2. So the first index says that if the first index is the same for this edge, it means that these are twins. So this E11 and E12, E42, E41, E22, E21, E31, E32. Okay, and the vertices V1, V2, V3, V4. Okay, so these are all the entities I have. I have 4 vertices, 4 edges, and 2 faces. Now I'm going to show you what each of these, I'm going to have a record for each of these entities and what I need to store in those records I'm going to show. Yes?
Bir konvensiyon var mı? Mesela 1'leri takip ederken 3, 1, 1, 1, 4, 1 hani yukarı olmuş. Yani clockwise mesela 1'lere.
Oh, okay. Actually, then this, if it's clockwise, then it should be the 1. Yeah. I think we should have such a. For this one, we may not, since this is not a, this doesn't correspond to a cycle. This is not a. outer or inner boundary cycle, we may not define which one is 1, which one is 2 for this one, but we should have such a convention for these ones. So for example, for the one that goes counterclockwise, we'll name those half edges with 1, and the counterclockwise ones are with 2. But the book did not do it, I guess. It said, yeah. Yeah, the book does not follow such a convention. It goes 1, 2, 1. I mean, it just arbitrarily gives the second index of these edges are arbitrarily given in the book. But it's, I agree with you, it's better to follow a convention like this. Now, for the vertex, for the vertices, we need 2 information. We need its coordinates, and actually the coordinates are the only thing that is going to be something physical in this record. I mean, that shows their position in this plane. So for each vertex, we are going to have its coordinates and also the incident edge. And the incident edge is going to be, we are going to have just a single edge for this, for vertex. For example, for vertex 1, it's going to be E11. Okay, so E11, this one, is going to be the incident edge of this vertex. You may argue, so why didn't we also say E32 as the incident edge of vertex 1? We are going to only store, let me just verify that. We only need actually an arbitrary half edge that V has as its origin, because having a single edge here, okay, we just need, by using just E11, we'll be able to, for example, we'll be able to associate, we didn't associate E32 with this. However, we are going to have V1 as E32's origin. Okay, so we are going to, we need this just arbitrary edge starting from this vertex to traverse, to complete the traversal starting from V1. So it's just an arbitrary, it is a pointer to an arbitrary half edge that has V as its origin. We don't need all the, we don't need an edge list here. We'll be able to complete all the operations with this information. And for face records, for face F1, for example, it has an outer component and a list of inner components or inner bound. It says component, we can say also say boundary. Okay, so the outer component, the outer boundary of face F1 is nil. It doesn't have an outer boundary, and its inner component is, we are going to have a pointer to an edge, which will able to help us to traverse this inner boundary in clockwise order. So E11 is an edge on the inner component of this face F1. Okay, if you start with E1, you can, by following its next edges, you'll be able to construct yourself the complete inner component of face F1. If it has multiple inner components, we have pointers to arbitrary edges in each of these inner components. So to indicate an inner component, all we need is an edge on that boundary. And clockwise edges gives us inner components, and counterclockwise edges give outer components. So for F2, for example, all we need is, for example, to have something like E42, okay, as its outer component. And as its inner component, it's nil. It doesn't have inner boundary. Now, for each half edge, the half edge records are going to be like this. We are going to, for each half edge, like for example E12, or let's have, for example, E32. For each half edge, this is an example. For each half edge, we are going to store its origin. For example, E32 has its origin V1. And we are going to have its twin, which is E31. We are going to have its twin, and we are going to also store its incident phase. Incident phase is the phase that belongs to this E32. E32 belongs to phase 2. Okay, so E32's incident phase is F2. It's the outer boundary. It's on the, so this E32 is on the outer boundary of F2. What about E31? If I look at the record of E31, what is its incident phase? F1, because it's the inner, E31 is the inner boundary on the inner boundary of F1. So its incident phase, E31's incident phase would be F1. So actually, by looking at twins, for example, these two twins, we can also find what? Neighboring faces, okay? If you want to find out what are the neighbor faces of, given a boundary, for example, if you want to find out all the neighboring countries, for example, of a country defined as a region, all you need to do is, by walking along its outer boundary, look at all the twins and look at which these twins are associated with as face. It's going to give you the neighboring faces of these edges. So this representation allows us to make really interesting queries very efficiently. We have the incident phase. So this is the twin. So twin, origin, incident phase. And we also have pointers to the next and previous edges. So the next edge of E32 is E42. And the previous is E12. Okay, so we have these records for these faces. Sorry, it's very, I wrote it very badly. So this is the edge record, this is the face record, and the top is the vertex record. So for each vertex we have coordinates and an arbitrary incident edge, and for each face we have the single outer component, a pointer to an edge, an arbitrary edge on the outer component, or a number of pointers to a number of inner component edges. If it doesn't have any hole in it, just nil. And for each edge, we have the origin vertex, the twin of this edge, its incident phase, and its next and previous edges along the border. So this is our doubly connected edge list representation, which is able to represent any planar subdivision consisting of finite length lines, consisting of line segments. These line segments are converted to these half edges to represent the region. Now, for example, let's try to represent this hole in a hole type of subdivision. What will happen? I'm going to use triangles, which are the smallest bounded cycles. that I can have. Okay, V1, V2, V3, V4, V5, V6, V7, V8, V9. As you can see, to label the vertices, I don't have any constraint as to the order of vertices. Okay, for example, in OpenGL, if you're defining these as polygons, you need to have defined the vertices in counterclockwise order. But the double connected edge list does not have this restriction. The vertices can be any order. The thing that defines whether it's an outer boundary or inner boundary is the order of edges. So when you label the vertices, you can give them any arbitrary order you want. Now, I have 4 faces. F1 is the unbounded, and this make this F2, F3, and F4. And I'm going to name some edges now. So this one, the counterclockwise order, is the outer boundary. So let's name it, for example, E11, okay, E21, E31. So the face record F4 is going to, so this is F4, inner, sorry, let's use the same thing, outer, inner. Its inner is nil, and its outer is going to have a link to E11 or E21 or E31, any of it. So this is for F4. Now, I'm not going to name the twins of this because it's going to make the drawing very complicated. I'm just going to write for F3 this. So let's name the edges of this as well. For F3, let's name E41, E51, and E61. And this one, E71, E81, and E91. Now, for F3, its outer boundary is going to be like E41 or E61, any, or E51, any of them. Let's say E51, for example. And its inner boundary is going to be the twin of E21, for example. Okay? So its inner boundary is the twin of E21. It has one inner boundary for F3. For F2, its outer boundary is, for example, E71. And its inner boundary is twin of, for example, E41. I'll have these for the inner and outer components, and for F1, for the face record F1, its outer component is nil, and its inner component is twin of E7. And this is not a unique way to store these things. I mean, you could have arbitrarily choose any 3 of these E71, E81, or E91 edges to represent the inner component. So any edges along any single edge, any arbitrary edge along the boundary is enough for us to compute the whole inner boundary. All we need to do is to traverse, starting from this twin E71 is going to be this. Starting from this twin, I have its next pointer. Its next pointer is going to be this. Its next pointer is going to be this. Until we complete a cycle, we complete a loop, I can continue following their next pointers and come to complete this inner boundary. Now, one thing that is difficult, we need to be careful, is that given an arbitrary So given an arbitrary cycle, can you understand whether it's an outer boundary or inner boundary? So we are going to be faced with this problem when we are actually computing the overlay of subdivision. So I'm going to leave this problem for next week. Okay. So to this week we only seen the general description of the doubly connected edge list, what we store in this data structure. Next week the problem we are going to be dealing with is given two such data structures, two different subdivisions of the same plane. Okay, the same blackboard, for example, is divided in two different ways. One of them may be consisting of vertical lines, one division. The other division may be horizontal lines. For example, they may say that, okay, we may color it from in grayscale from black to white in this vertical strips. And in the horizontal strips, we may have maybe from dark red to light red. These regions may indicate different things. And our goal will be to compute the overlay of these two subdivisions, which is going to define a new subdivision. For example, we are going to have regions like this. So it was horizontal, between the horizontal strips and vertical strips, we are going to have a new region, which says, for example, medium red. This is medium red and gray, for example. This region is going to have two properties, two attributes coming from one subdivision and the other subdivision. So this is going to create a completely new subdivision. So how do we correctly create a data structure, a corresponding doubly connected edge list for this new overlay? What is its vertices going to be? What are its edges? And what faces it's going to have? So can you compute all these correctly given two different subdivisions? The overlay problem is this, and we are going to talk about this next week. And in the first hour, I've planned to finish this, and in the next hour, we are going to start polygon triangulation. And the practical problem we are going to be dealing with is the art gallery guarding problem. So given a two-dimensional art gallery, what is the minimum number of cameras that you need to put at the vertices so that you cover every region within this art gallery? Okay? So we are going to try to solve this problem next week. No homework for next week.